Okay, hi everyone. My name is Shay. I lead a data science and engineering team in Microsoft Education. And today I'm excited to talk to you about how we're using language models to improve literacy. And to set the stage, I want to start by presenting two related products that are in the Microsoft Education suite and are available for students. It's being actively used by students, by millions of students worldwide. The first product is called Reading Progress. And this is a product that's used for assigning reading passages by educators to students. So this is educator driven. As you can see, this is a part of Microsoft Teams. Microsoft Teams is actually a third of the usage of Microsoft Teams is driven by education. You can see that students can actually control whether they want to share, when they want to share the reading session. And AI analyzes and tracks results across different dimensions. See that we tag accuracy and we tag prosody and different aspects of speech. And this offering is packed with AI. It's driven by Microsoft Cognitive Speech Services. It measures automatically pronunciation. It measures speech disfluencies, and it supports over 100 languages across accents and locales. So the second product that I want to highlight is a companion, is a companion to Reading Progress that lets students practice specific words. This is called Reading Coach. And Reading Coach is an application that focuses on building phonemic awareness and helps improve vocabulary. It's student-triggered opposed to Reading Progress, which is educator-triggered. And it allows for a personalized and self-paced learning on individual challenging words. As you can see here, it allows a student to practice a specific word that they found challenging and to break that word into phonemes and to learn how to pronounce the word correctly. Now, naively presenting these challenging words would just be, taking the words that the students got wrong and presenting those for the student to practice again. But that type of recommender system is biased in the sense that it's offering less of an experience or a less quality of an experience for stronger students that get less words wrong. And also it's less engaging and serendipitous because at some point the student would finish the word bank and then the experience would be over. So the first thing that I want to show you is that how we use the recommender system to improve over this naive approach. And what we did is we relied on collaborative filtering, and we built a model that maps students and words to a shared latent space, such that proximity in the space means that certain words are challenging for the same underlying reasons. And in essence, what we do is we can recommend more challenging words to David, for example, on the right here, by actually relying on words that were mispronounced by Sarah. And these are words that David didn't practice on yet. We didn't see whether or not they found challenging. So this model reinforces itself as students continue to practice, and it provides means to meet students at their level of proficiency as they improve. Now, these are nice capabilities, but I want to highlight some of the product gaps that we had in our product and show you how we're closing them with large language models. So when we think about the skill of reading, it's traditionally broken down into this hierarchy of more foundational skills. Fluency, for example, is defined as the accuracy and speed of reading without conscious attention to the mechanism of reading. While comprehension at the top of the pyramid is the ability to understand and to retain information given in the text. Reading Coach that I showed you, the second product that I showed you, focuses on the bottom of the pyramid here. And it helps improve the understanding of the mapping of graphemes to phonemes, which are the letter elements of words, into the sound elements that you need to express to read them. And reading progress focuses on the next two levels, focusing mostly on fluency by measuring the reading rate, the accuracy, and different influences and prosody. Now let's talk about two gaps. Reading Coach, as I mentioned, is already personalized. Students get words that are recommended to them based on their successes and mistakes. But Reading Progress doesn't have any AI personalization. For any personalization, the educator would need to manually and laboriously go over each student and assign them their own task. And this is one gap that we wanted to solve. And the second gap is a product gap related to comprehension, which I'll talk about later. But let's focus first on reading progress. So naturally, when we got this new technology of large language models, we thought immediately of trying to tackle personalized reading passages in reading progress by doing reading passage generation. I wanted to talk a bit about the challenges there. This feature was announced in preview in March. It's among the first wave of Copilot announcements. This is our humble entry. We're a small team, so it was a huge success to be able to get a feature out there and announced by Microsoft along with the big players, the Copilot players. And what we did here is we leveraged the recommender system that I showed you earlier to generate personalized passages. So an educator would be able to pick from a list of recommended words, just a combination of words, and generate a reading passage. And you'd be able to edit that passage and modify it according to their needs. And I think that this is a nice concept. I'm sure you're all familiar with tool augmented language models, but I'm not sure how many of you are familiar with Rexis augmented generation. So this is, I think, an interesting approach to be able to personalize the results given by large language models. And this capability is currently being baked into different product surfaces across Microsoft. And the UX will look differently in different places. So our goal was to unlock the values that LLMs have to offer for education, but we really needed to do this responsibly, especially since education is considered a sensitive use domain, which is catering to underage people. And responsible AI certification in Microsoft is a mandatory and strict process. It includes red teaming exercises where, as a group, we meet to try and manipulate the model to provide inappropriate responses. We're trying to see that users can't break it, in essence. Offline. Okay, so again, so passage generation had this unique combination of properties that helped us quickly navigate through these assessments. First of all, it's educator facing, an educator in the loop. So essentially, the model generates text, which the educator needs to evaluate and validate before assigning to students, which reduces the risk surface of exposing to underage people. Next, hallucinations are tolerable because actually we want passages to be creative. We want them to be diverse and engaging, and factuality is less of a concern. There are no free inputs, free parameters. We limit the inputs to the model to those list of words, and the prompt is a template. So this limits the types of generated outputs from the model and allows us to have more confidence before releasing it. Next, we developed several guardrails internally using prompt training techniques. What we did is the first guardrail I'm going to dive into both of these in the next slides, but the first one is readability adaptation, where essentially we're making sure that the generated texts are age appropriate. And the next one is using debiasing chain, which is doing things like randomly swapping the gender of the protagonist, adapting locations and characters and cultural references to be relevant to the user's country, and making sure that the generated texts are appropriate. And the last, this is a separate bullet because this is also a huge investment on our side, is we have our own extended content moderation stack, which is more strict than what you get out of the box if you just use Azure OpenAIs. So what we do is we leverage several internal services beyond Azure OpenAI. We also leverage Azure Languages Services, and we also ask GPT to self-criticize its outputs whenever we have any words that we have low confidence in them being context-dependent offensive. So these are just some of the challenges, and I want to dive into, first, let's start with cultural localization. This is an example of how do we get the passages to be more engaging and to speak to the world of each student. This is just an early experiment. As you can see, this is using the ChatGPT UX. And what you see here is a very simple prompt chain where we ask the model to start by just building some reading paragraph, some story about a child's first day at school. And then we ask it to rephrase the above such that the resulting text is still in English, but mentioned names, places, and cultural aspects are more appropriate for Chinese readers. And I highlighted the differences between the two passages. What you can see is, for example, names. Originally, the model would just pull from its distribution the most likely name, and it's very Americanized. You see, the girl's name is Lily, the teacher's name is Mrs. Smith, and they're learning their ABCs. And once you tell the model to be more appropriate for Chinese readers, the girl's name is Mei Mei, the teacher is Mrs. Chen, and instead of ABCs, they're learning their characters. I think this is a nice example of GPT's ability to self-criticize also in this aspect. Let's look at another example. Here I want to talk about readability adaptation. So first, readability is a set of scores that are psycholinguistic. These are metrics that quantify how complex a text is to read. And it's usually a function of the length of the text, the number of syllables per word, and average lengths of words. And it's relying on qualitative studies of what words are typically acquired at what age for children. And as you can imagine, different texts, for example, Harry Potter is more appropriate to a reading level of, let's say, between 6th and 9th grade. And an academic paper is like above 15. So this is just one such metric called Flesch-Kincaid. In this figure, this is a blog post that I'm referencing here at the bottom. The authors calculated different metrics of readability on different large language models. And what you can see here is that different models have this typical audience that they're adapted to. So on the y-axis, you have the readability score, one of these metrics that I mapped for you to the relevant grade levels. And you can see, for example, that GPT 3.5, which is this one here, it's appropriate for the texts that it generates are appropriate for college students mostly, or maybe a little bit above 12th grade. So in our products, the core demographic are students from 3rd to 12th grade. So this is not covered here, as you can see. Models need to be coerced to be more age specific. So the way that we tackle this problem is that we're trying to we have this game. We play a game with the model. What we're doing essentially is we want to optimize on the readability score. So we're using the model as a derivative-free optimizer. Essentially, what we're doing is we're telling the model, we start from an initial passage. We tell the model using in-context learning in the prompt, we tell it, please generate a text that's appropriate for this grade level. Then we measure whether or not the model was successful using these readability metrics. And we repeat until convergence, we evaluate the readability, and we ask the model to either increase or decrease the difficulty until it converges. At the end, since we did many attempts to evaluate the model. We can just pick the best one that we've seen from this activity. So a nice thing here is we're using chats because essentially we can use the conversational memory of the model to kind of act like a momentum mechanism that you have in optimization. This helps the model adapt the magnitude of change. So we can tell it make it harder or easier with respect to this context of the previous attempt that we had. So this is a benchmark of we ran an experiment to evaluate this method. In blue here, you can see the generated passages before we applied this readability adaptation mechanism, where on the x-axis, we're showing the grade level error. So we asked it to generate, for example, a passage that's appropriate for a third grader, and then it's generated something that's appropriate for a fifth grader. Then that would be an example that lands in this bucket, in this histogram. So the blue bucket here. After we run several iterations of the optimization, the end results for these passages are described in this histogram in orange here, the final error. You can see that it's much more well suited to our target audience because it's the error, the expected grade level is much closer to the required grade level in the parameter. On the right side, I'm showing you the number of iterations that it took for us to converge for each passage, and we're actually capping this at 3 iterations, but essentially we could probably continue this process until we converge to the expected grade level. Okay, so this was so we've covered AI personalization for reading progress. I've shown you some examples of the type of things that we're using internally to make things grade appropriate. And now I want to highlight the second product gap that we're closing with comprehension quiz generation. And to bridge this gap, what we're doing is we're releasing support for automatically generated comprehension questions and answers, along with automatic grading and monitoring of student results. So here you have the interface for the educator. When they assign a reading passage, automatically we're going to, behind the scenes, to take this reading passage and build a quiz based on this passage. And we're giving the educator the ability to edit the quiz. Ouch. We're giving the educator the ability to edit this quiz and validate that the results, validate that both the questions and the distractors are accurate. And they can add their own options, they can add their own questions and validate the model. And essentially this keeps the educator in the loop. Next, the student would get this sort of interface where when they're finishing reading an assignment, they're asked questions about what they've read. And this gives the educator the ability to automatically evaluate comprehension. So I want to talk about some challenges here. And I think one interesting challenge in reading comprehension is that we want to generate a structured output, which is a quiz, with a limited budget. So we have our token budget. This is, for example, 8K in the chat turbo model. And we have to feed the system prompt, which basically tells the model, build a quiz, it's appropriate for children, etc. We also have to feed in the entire reading passage, which could potentially be long. And then this is the slack. This is the remaining token budget for actually generating a quiz. So we wanted to optimize essentially the system prompt so we're not wasteful in the amount of tokens that we use. And here, what I want to show you is, I'm not sure if you're all familiar with Langchain. It's a Python SDK that does different chaining and agents and different tricks on top of GPT or other language models. And Langchain has this notion that's called an output fixing parser. You can use Pydantic to take a Python class and automatically implant instructions in the prompt, in the system prompt, that translate this class object into a JSON schema where different properties of this class, you can also validate their typing using Python's type hinting. And that is very wasteful. I mean, when you take a large object, when you have these complex property names, and you just map everything to text, you get a lot of redundancy, especially because for our example, we're generating a quiz, which is everything is string. So I don't really need the type hinting. I just want strings back. So to reduce the amount of tokens that we used here, what we did is we just used a very nice shorthand for everything. So we tell this is a snippet that's part of the prompt, of the system prompt. And in the snippet, we're telling it to build this quiz as a JSON that conforms to a schema. And for example, just stating MCQ, which is shorthand for multiple choice questions. This is commonly used shorthand. And then giving examples of what we expect to be one multiple choice question. It's composed of a question, an answer, and distractors. Just using those shorthands really helps conserve tokens. And the same thing we did with true-false questions or open-ended questions. At the end, what we had to do to make this work with Langchain was just to override this parse object method that's part of the quiz objects. And I'm not showing you everything as part of this, all the code as part of this snippet, but using it is very simple. You just create a pydantic output parser that gets this as an object, the quiz object. And then you use the output fixing parser on top of that pydantic parser. And what this does is it helps the model evaluate whether the result is parsing correctly or not. And it can correct itself and can continue to query GPT in case things are not parsed as a JSON. Okay, so to finish up, I'll just highlight some of the work that we're continuing to work on. Of course, quality is an ongoing task. We're still measuring and improving, and we're evaluating. It's especially difficult because we're not students. We don't know how students would react to the results. We need to somehow release something out to the world and then measure how that works. So we're working in private previews with educators across the world. The next thing that we're working on is we're trying to enable student-triggered scenarios. So what I've shown you here is the only student-enabled scenario is the reading coach, but we want different experiences that are gamified and that are working responsibly, because releasing these models out to students is a challenge. And the last piece here is lowering costs. So GPT is expensive. EDU is not really a money-making business for Microsoft. So we also need to somehow compete with these large initiatives internally, to compete with these large initiatives of co-pilots. And getting GPU allocation is a challenge inside Microsoft. So we're I think in the same boat as everyone, as every startup out there. Getting access to SLA capable endpoints, to GPU capable endpoints is a problem. So what we're doing to try and mitigate that is we're actually working on distillation of models, and we're using GPT to generate passages, and we're using GPT-4 to label them in terms of quality. And then we're essentially fine-tuning smaller open source models to try and conserve GPUs. And with that, I'll finish. Thank you.